everyone, here are your 1.9 notes. So what we're going to be getting into for the last section of Unit 9 is how we're going to incorporate all of these different concepts with functions into real-world settings. So this whole entire lesson is about word problems. So just reading the paragraph at the top, it says, in real-world settings, we need to construct functions by translating verbal descriptions into the language of mathematics. We are learning to assign meaningful variables and symbols that will represent both independent and dependent events. So let's go ahead and explore some situations where we're going to create a function or a rule that represents real-world events. So the first two are quite easy. We're bringing back our concepts of geometry into play. So number one, it talks about the perimeter of a rectangular garden. That's 84 feet. So let's go ahead and turn that directly into an equation. All right. It's pretty frigid up here in my third floor, so who knows if my computer... Okay, here we go. Okay, so do we remember how to find the perimeter of a rectangle? Your perimeter of a rectangle, the formula is P equals 2 times the width plus 2 times the length, right? And they're telling us in that first sentence that the perimeter is 84. So here I have an equation of 84 equals 2W plus 2L. Then we're told to express its area as a function of the width. So remember, area is equal to length times width. So now I want my function to be in terms of only the variable width, all right? Which means right now I have a length in there, but how can I turn my length variable into an expression that incorporates just the width? Well, that's going to come from the perimeter equation. So can we solve that equation for L? Okay, so technically we could go ahead and divide everything by 2 right away, but the right move would be to factor out your 2 is equal to 84 and divide by 2, which gets us 42 is equal to W plus L. Subtracting W gets us 42 minus W equals L, right? So now I can plug this expression in place of our length into that function, and we get 42 minus W times W. So simplifying that by multiplying, distributing, gets us 42W minus W squared. So now we just expressed the area of our function with width. Okay. All right, so number 2, the volume of a right circular cone is 1/3 pi r squared h. If the height is twice the radius, we want to express the volume V as a function of the radius. So let's go ahead and turn everything into what we need to. So we were given volume. Volume is equal to 1/3 pi r squared height. We were just told that height is equal to 2 times the radius. So now we want to express the volume as a function of just radius. So I want to get rid of my height right here so that it's in terms of radius. So plug that in. So my volume in terms of r is going to be equal to 1/3 pi r squared times 2r. Simplifying that, volume in terms of radius is going to be, what, 2/3 pi r cubed. Cool. So now we should be able to use that for part B. So we want to find the volume of a paper snow cone cup whose radius is 2 inches. So volume in terms of radius, but now my radius given is 2. So we're going to plug in 2. So 2/3 pi times 2 to the third. 2 to the third is 8. 8 times 2 is, so we get 16/3 pi inches cubed would be our exact answer. Our approximate answer, when we put that into the calculator, you should get 16.755 inches squared. So our volume of a 2-inch radius snow cone cup is approximately 16.755 inches cubed. Okay. All right, so those were quite easy because maybe we remember our formulas from geometry. So now our next chunk is going to get us into business and economics, and it's important that we get into these types of problems because they're becoming more and more frequent on AP Calculus exams. So it's kind of good to get them in your brain for when you get there. So in the business world, we're concerned with sales, costs, revenue, consumer demands, and profit. Your revenue R is defined as money received for the sale of X units sold at the retail price of P. So we get the formula R equals P times X, right? Which makes sense. If you're selling a shirt for $15 and you sell 10 of them, you just made a revenue of 150, right? And then the law of demand, which comes from our economics courses, tells us that the price and units sold are related. So specifically, as one increases, the other decreases, which that makes sense. The more you jack up the price on an item, probably the less units you're going to sell, right? So here in example 3, we have the demand for tickets to a local water park is given by the function P equals 75 minus 0.02x, where P is the price of ticket in dollars, and X is the number of people going to the park at that price. So part A, what price would provide attendance of 3,000 people? So we're going to figure out what price we would get when we have 3,000 people. Okay, so X is the number of people, so 75 minus 0.02 times 3,000 gets me a cost of $15. So my price for a ticket to get the 3,000 people should be at $15. So now, what is the total revenue at this ticket price? Now remember, up above, it told us that our revenue function was P times X, or XP. That's the way I'm going to write it out. Okay, so I guess we don't need to write XP. Let's just keep it PX. Why not? We just found what our ticket price was, right? Our ticket price was $15, and our X was our number of people we were selling it to. So if I had 3,000 people at $15 a ticket, that's going to get me $45,000 would be my revenue. Okay, so now we want to write the revenue function as a function of attendance, X, at the water park. Okay, so my revenue, so this is kind of like our general setting. I used part B because I knew how much my ticket cost was and I knew how many people I could be, or was going to come and buy the $15 tickets. So for C, I want to write my revenue in terms of X. So I need to get rid of P, right? Well, what did we say up here in our original part? What was P equal to? 75 minus 0.02x. So instead of PX, we're going to do 75 minus 0.02x times my X. All right, simplifying that gets me 75x minus 0.02x squared would be our general form with revenue function as a function of attendance. Okay, that little squared there got lost. Don't lose that. All right, very good. Moving on. Nope, I don't want to do that. To the next one. Example number 4. Example number 4 gets us into a little bit more complicated thinking, but not too terrible. We have a skateboard designer who has a fixed monthly cost of $9,202 and a variable cost of $18 for each skateboard produced. The skateboards sell for $125 each. How many skateboards should the designer produce and sell each month to break even? What then would be the total revenue at the point where the designer breaks even? So right away I see that break even, which means we're probably going to be setting something equal to each other. What are we going to be setting equal to each other? Well, the cost, we want to see when does that equal out your sales or your revenue, right? So when are those equal? Because that would be my break even point, right? So what would be our cost function? So my cost function is I have a flat rate cost, our fixed monthly cost at $9,202 plus $18 for each skateboard produced. My revenue function, I'm not going to set these equal yet just so we can get them written down, remember is X times P, right? Okay, and what is our price? Remember, P is your price, 125, so 125x. Just going to put the 125 in front of the x. So now I want to know, when does R of x and C of x equal each other? So C of x, when does that equal R of x? So here we go. 9,202 plus 18x. When does that equal 125x? All right, I'm going to jump right to the answer because we all can do that math, I would assume. We get x to be 86. So that means we need to sell 86 skateboards in order for me to break even. Skateboards to break even. So anything beyond those 86 skateboards, so 87, then I'm going to start bringing in a profit, right? Anything less than 86, I'm not making a profit yet. I'm still in the hole from the cost of making everything. Okay, so what is going to be the total revenue at that point where the designer breaks even? Okay, so revenue, remember our revenue function was R of x equals xp. And we just said that my price was 125. We need to sell 86. Multiplying that out gets me $10,750. So that would be the total revenue at that point. So we got money coming in, we've got money going out with costs. I'm going to get to that 10,750 point, but there I'm still not making any money. There's no extra revenue happening. Beyond that is when I'm making actual money. Okay, cool. I don't know why I'm saying cool all of a sudden. All right, now number 5. This is a good crazy calc one. They love this one in calculus. So let's see if we can get our brains wrapped around it. Okay, so here we have in a diagram, you can see where point P, they have x comma y, is on the graph y equals x squared minus 1. I just want to make sure my calculator is turned on. Yep, it is. Oh, I already have it already in. Perfect. Okay, so our goal is to find an approximation of a point on the graph that is closest to the origin. So let's think about what's happening here. We've got an infinite number of points, right, on our graph. I want to find which one of those points is closest to the origin. Okay, now again, remember that quadratics are symmetric. So whatever point would be on this side, it would be the same on the other side. Okay, so let's go ahead and do some thinking. So we have our y equals x squared minus 1. We are told we have a point on the origin, so that's 0, 0. So now let's make our right triangle. So here's my right triangle. Drop it down. Do you see how our distance represents the hypotenuse, right? So if we think about the distance formula from geometry, where your distance is equal to the square root of some x minus some second x, in this case our second x is 0 because of the origin, plus some y, or y sub 2 minus y sub 1 minus my y sub 1, which again is going to be 0 because we have the origin. So simplifying that gets me d is equal to the square root of x squared plus y squared. Okay, so now we got to express the distance d from P to the origin as a function of x. Well, right now I have y in there. I need to turn that y into an x. Well, remember up here, we said y is equal to x squared minus 1. So let's go ahead and put that in. So d in terms of x is going to be equal to the square root of x squared plus, now let's substitute in our y, x squared minus 1 squared. All right, so let's go ahead and do that math for multiplying that out. That gets me x to the 4th. My middle number is going to come from x squared times negative 1 times 2 is my little trick that I do. So x squared minus 1 is negative x squared times 2 is negative 2x squared. And then squaring a negative 1 gets me plus 1. Bring down my x squared here. Simplify, so d of x is equal to the square root of x to the 4th minus 1x squared plus 1. All right, so there we expressed the distance d from P to the origin as a function of x. So I don't have any y's in there anymore. So that represents this distance, right? Okay, so now it's asking us to use a graphing utility to graph the function, so our new function, and then find the value of x where d has a local minimum. Okay, so we want to focus just on the positive version because the negative version would just be the negative of it because it's symmetric, right? Okay, so when we go ahead and do this, oops, I didn't want to get rid of that. Bring that back, and then we do that. Okay. So when we go and do this on our graphing calculator, I typed in the square root of x to the fourth minus x squared plus 1. I'm going to go back to my standard form. This is what it looks like. Okay, so it's kind of, you can remember our quartic graphs are very similar to a quadratic graph, but it has that little W shape in the middle. I'm going to zoom in so I can kind of see what's actually happening down there at the bottom. So I'm going to move my cursor up to my y-intercept, and now I can see it a little bit better. And the graph actually provided for you right here, where it just gives you that right-hand side. So remember, that represents our distance from point P to the origin, right? And this problem is asking us to find the minimum or the smallest distance from point P to the origin. So this graph right here represents all those different distances of point P that it could possibly be to the origin, right? So I want to find the smallest or the minimum distance. So my calculator can find a minimum value on this graph for me. So you can kind of see how your minimum value is happening right around here. So I'm going to hover over here. If you guys remember how to find minimums with our calculator, I'm going to hit second calc, go to number 3. Oops, I guess that moving the cursor was unnecessary. Okay, so that looks like a good left bound. I'm going to hit enter. I'm going to go beyond where I think the minimum point is, hit enter, and then we get the 0.707107479. So that is my minimum distance. Now if we go back to this problem, and they have the graph right there, it is for you. So when I have a minimum value, right, so my x is going to be a minimum at 0.707, that looks good, which would also be the same at negative 0.707. All right, now, you don't know this yet, but we'll eventually get there when we get to our unit circle with trig. That decimal is equivalent to the square root of 2 over 2, and this decimal is equivalent to the negative square root of 2 over 2. So if I wanted to actually figure out what the coordinates, exact coordinates of point P is going to be, I'm going to plug those values back into, so substitute back into our equation, right? So our distance at, let's do the square root of 2 over 2, it ends up getting you to 1/2, negative 1/2. Actually, no, we're not putting it into our distance, right? Oops. Am I putting that back into the original, right? So the negative, so square root of 2 over 2 squared minus 1 is going to be 2 over 4 minus 1. Yeah, that's where it comes from, negative 1/2. Right, because I'm trying to find the ordered pair on the graph y squared minus 1. So my minimum x value occurs at the square root of 2 over 2. When I plug that back into the original y function, I get negative 1/2. So my point that is closest to the origin is going to be the square root of 2, negative 1/2. And then, since it's symmetric, negative root 2 over 2, negative 1/2. That's a good problem. And you're going to love them when you get to calculus. Okay, here we go. Moving on. Example number 6. Grain is leaking from a hole in a storage bin. At a constant rate of 6 cubic inches per minute, the grain forms a cone-shaped pile on the ground. As it grows, the height of the cone always remains equal to its radius. If the cone is 2 feet tall now, how tall will it be in an hour? Okay, so this is another good one. So now we're going to bring back that volume formula for a cone that we used on the snow cone problem. So remember that was V is equal to 1/3 pi r squared h. Okay, what else do they tell us? That we have a constant rate of, so my rate is equal to 6 cubic inches per minute. Then it's making a cone-shaped pile on the ground. As it grows, the height of the cone always remains, ooh, that's a good one. So my height always remains the same as its radius. So if the cone is 2 feet tall now, so my height is 2 feet tall, but I'm going to convert that to inches just because notice my rate is in inches. So I probably want to keep everything in inches. So 24 inches. How tall will it be in 1 hour? So we need to figure out what's going to be the volume now, right? And then we need to know what the volume is going to be later. And then from there, we should be able to find the new height. Is what I'm thinking we need to be doing. Okay, so let's go ahead and convert this to be a function of h, since we're talking about we want to find height, though height and radius are the same, right? And this is rate, not radius. That might get confusing. Okay, so our function in terms of just height gets us 1/3 pi height cubed, right? And we were told that our height is 24 inches. So 24 inches cubed. All right, I'll do the math for us. So that gets me, so my exact answer is 4,608 pi inches cubed, which is equivalent to 14,476.46 inches cubed. You can trust me on that math. Did it twice. We should be okay. All right, so this is my volume now. So this is my volume now. So now I need to find my volume 1 hour later, right? So if it has a rate of 6 inches, so we're finding 1 hour later, 6 inches per minute. So in an hour, how many more cubic inches are going to get added? So after 1 hour, and we're doing 6 cubic inches per minute. We have 60 minutes in an hour. So that means we're going to be adding 36 cubic inches within that hour. Okay. So my future volume, I guess we can call it, going into the future, is going to be equal to that 360 plus the now, which was 14,476.46 inches, cubic inches. So my volume in terms of height is going to be, what does that get me? 14,836, and just go to 0.5 cubic inches. Okay, so that would be the future volume an hour later. So now can I figure out what the height is going to be of the grain? I hope so. All right, so I'm going to clear this space off to the left here. We're going to go up here. So now I'm going to take my new volume, 14,836.5, and set that equal to pi, or 1/3 pi h cubed. And then doing that math gets me, so timesing this by 3, 836.5. Gets me pi h cubed dividing by pi. And then I would take the cube root of that answer. So the cube root, that's where the solving comes from, which gets us our height to be approximately, I think it ends up being 24.197 inches. Okay, so after an hour, we gained about 0.197 inches, so about 0.2 of an inch with that rate. All right, that's a good problem. I like that one. All right, example number 7, Hooke's law. Hooke's law for springs states that the distance of a spring is stretched or compressed varies directly as the force of the spring. A force of 275 newtons stretches a spring 0.2 meters. So remember our direct variation, that's y equals kx, right? So now I'm going to put it into context. So it's y varies with x. So the distance is varying with the force, it looks like. And we need to figure out what that constant rate is. So we're given that a force is 275. The distance is 0.2 or 2/10. So that gets me k is equal to 1 over 1,375 when you solve that out. So that gives me my generic form of distance equals 1 over 1,375 times the force. So how far will a force of 620 newtons, so plug that in for F, 1,375 times 620 gets you, sorry, this chair is really wobbly, 0.45 meters will be how far the spring will stretch. Okay, so then for part B, it's asking us what force is required to stretch the string 0.1 meter. So 1/10 of a meter is equal to our constant, which is 1 over 1,375 times F. And then when you multiply by the reciprocal there, you get 137.5 newtons. That one's pretty easy if you guys remember your direct variation problems or equations. All right, and then on to the back, let's go ahead and finish up with some regression models. So please have your calculator handy because this is all calculator work. So example 8, the U.S. bottled water producers' revenue in billions of U.S. dollars from 2005 to 2012 is shown in the table at the right. We're going to use a graphing utility to write an regression equation. The time in years is given by t. So the first thing you do is get your calculator out, and we are going to create a list. So hit your stat button, hit enter, and I have all sorts of stuff in mind because I teach statistics and we are always doing lists. So let me clear these out. If yours are not clear, if you highlight over the list name, oops, and hit clear and then enter, it'll clear everything out. So let me go ahead and clear all this stuff out. I should have just did a clear all lists. That would have been a lot quicker. Okay, that should be enough. Okay, so now under list 1, we're going to put in our years. And notice here how they're telling us to let t correspond with year 2005. So we're not going to put in 2005. We're going to type in 1, hit enter. 2 is 6, 7 is 3, 8 is 4, 9 is 5, 10 is 6, 11 is 7, and 12 is 8. And then in list 2, we're going to put the revenue. So $10.01. Oops, too many ones. $10.86. And now we're doing, oops, I can do this faster this way, 11.55, and then 11.18, and then 1060, 11.07, and then 11.82. Oops, somehow I got off. 10.1, 1086, 11.55, 11.18, 1060, I missed 1069. 1069, 1107, and 1182. Okay, so hopefully you have your lists in and correct. So now it's asking us to, in step 2, create a scatter plot of our data and determine the best type. So to make a scatter plot, you hit second and y equals, and you're going to go into plot 1 and turn it on. And then you have a whole bunch of different types. The first one is scatter plot. We have line graph, histogram, bar and whisker plots, and this is a normality probability plot, which you'll learn about in stats next year if you take it with me. And then here we have list 1 is our X. I need to change my list 2 to my Y. So if yours are any different, you have to hit second and then 1, 2, 3, the numbers there get you your list names. Okay, and then what you're going to do is you're going to hit a zoom and then hit zoom 9 for zoom stat, and that's going to take you to the scatter plot. Whoop, and I just realized I have my square root graph there. Okay, let's go back. There we go. So what type of graph do we think it could potentially be? Does it look linear? Does it look cubic? I mean, I definitely see a bit of like curvature to it and not just straight. But I don't know. We decide which one makes the most sense. So to write your linear, if we want to come up with the regression line for the linear graph, you hit stat, go over to calculate, and then we're going to go to number 4, which is the linear regression problem. My X list is L1. Yours probably already says that. My Y list is L2, and then I'm just going to go down to calculate. If your calculator doesn't come up with that menu, that's okay. Just go to number 4, and then you'll just have to hit second L1, and then comma, and then second L2, and then hit enter, and then you should get this information up. If you're not getting an R squared and an R value, that's okay. We're not really going to be talking about R squareds and R's right now, so you'll be okay. But there's a way you can get that turned on with your diagnostics. Okay, so here is our information. We have Y is equal to 0.1, which I'm just noticing this is a little bit different than her Inspire data. Are you guys getting the same thing that I'm getting? So if we use that information, how do we turn that into our linear regression? So let me switch this. There we go. All right, so for our linear equation, I guess it's pretty close, right? 0.12 and 0.119. Okay, so we're gonna go with our answer. So Y is equal to, maybe you're getting the same thing she is, I don't know. So Y is equal to my slope, which is the A, so 0.119x plus 10.44. Looks pretty good. Okay. Now what I want to do is I want to come up with the cubic regression equation. So I'm going to have to exit out of this so I can go back to my calculator. So go back into that stat, go over to calculate, and now go down to number 6, or just hit 6, and go to cubic reg. Okay, so let's go ahead and go down and see what we've got. So there I get a function that is, oh, I just lost this one. So what do we say it was? Oh goodness, I forget. 0.119x plus I think 10.44. So cubic one, we have Y equals 0.046x to the third minus 0.629x squared plus 2.54x plus D 8.09. I get that in there? 9. Okay, again, a little different than hers, but not too far off. Maybe because she was using Inspire that it got really fancy. All right, so there's your cubic graph function, and there is your linear regression function. So now we're going to use our models to predict water revenues for 2018. So remember, our T equals 1 for 2005. So to get to 2018, that's going to get our T to be 14. So I would hope that everybody could figure out what that equation is based off of plugging it in, right? Is it okay if I just go right to it? I'm going to go right to it for you guys. So the linear was around $12.17 billion. And the cubic was around $49.28 billion. Okay, so which one would make the most sense in this scenario? Now again, the scatter plot's looking pretty cubic. It seems to be kind of matching that pattern if you look at her actual graphs with the lines in there. But if we think about the actual problem, it's talking about the U.S. bottled water production. I would not assume that the growth of water bottles grows exponentially fast. I don't know if maybe I'm missing out on something, but I feel like that's a slow growth production as opposed to something that's really quick. So usually when something grows very quickly and it's, like technology, that's really growing quickly, I would call that more of a cubic type scenario. I think a linear model makes the most sense here. So linear makes the most sense. Linear makes the most sense because this industry has slow growth. And we're going to assume that it's slow growth. right? So you might want to just make note if it's something that has quick growth, then we would go with the cubic, because the cubic, if you remember your cubic graph, it like shoots right up there as opposed to a slow, steady climb with the linear. Okay, so that concludes your 1.9 videos and Unit 1. Hurrah! You guys did it. All right, bye guys.